Assalamu alaikum. Today we want to talk about chapter 16, part 3, acids and bases. We start with 16.7, weak bases. Many substances behave as weak bases in water. Weak bases react with water, abstracting protons from water, thereby forming the conjugate acid of the base and OH-. Now, water is the solvent, and the most commonly encountered weak base is ammonia. And you can see here ammonia plus water to form. So ammonia abstracts a proton from water to form an H4 plus, its conjugate acid, and OH minus, the conjugate base of water, is formed. Now, the equilibrium constant expression for this reaction is Kb equal molar concentration of NH4 plus times molar concentration of OH minus divided by molar concentration of ammonia. Now, since water is the solvent, so it is omitted from the equilibrium constant expression. Now, Kb here is the base dissociation constant. Now, table 16.4 here lists the Lewis structure, conjugate acids, and Kb values for a number of weak bases in water. As you can see here, Kb can be used to find the molar concentration of OH minus and through it the pH. Let's go and see the following example. What is the pH of a 0.15 molar solution of ammonia? According to the equation we saw, and this is Kb. And Kb from appendix from table 16.4. So this sample exercise is the same. Calculate the concentration of OH minus in a 0.15 molar solution NH3. You can get the value of Kb will be given to you. So here again we have the equation, and Kb value is this. We construct the table. The starting concentration of ammonia is 0.15 molar, and H4 plus 0 or H minus 0. The expected change is minus x. This is plus x plus x. The equilibrium is 0.15 minus x plus x xx. Then we plug it here, or apply it to this formula. And here, since the Kb is small, we can neglect the small amount of ammonia that reacts with water as compared to the total NH3 concentration. That is, we can neglect x relative to 0.15 molar. So then we find the value of x, and x equal molar concentration of OH minus, and x equal this value, 1.6 times 10 to the minus 3. Also, you might ask to calculate the pH. You can calculate the pH of a solution of a weak base. Once you have the value of OH minus, you can proceed where we calculate the pH of a strong base. If the present sample exercise, we have seen that 0.15 solution of ammonia contains this concentration of OH minus. We find pOH to be minus log this and equal 2.8, and pH equal 14 minus 2.8, and the pH is 11.2. The pH of the solution is above 7 because we are dealing with a solution of a base. You can also look at the practice exercise, which says which of the following compounds should produce the higher pH at or as a 0.05 molar solution: pyridine, methylamine, and nitrous acid. Methylamine, because it has the largest Kb value of the two amine bases in the list. So the largest Kb will give the highest pH. Now we want to talk about types of weak bases. Weak bases fall into two general categories. The first category is neutral substances that have an atom with a non-bonding pair of electrons that can accept a proton. Most of these bases, including all uncharged bases in table 16.4, contain a nitrogen atom. These substances include ammonia and related class of compounds called amines. In organic amines, at least one NH bond in NH3 is is replaced with an NC bond. Like ammonia, amines can abstract a proton from a water molecule by forming an NH bond, as shown for methylamine. Anions of weak acids make up the second general category of weak bases. In an aqueous solution of sodium hypochlorite, for example, NaClO dissociates to Na plus and Cl O minus ions. The Na plus ion is always a spectator ion in acid-base reactions, which means it does not affect the pH. The Cl0 minus ion, however, the conjugate base of a weak acid, hypochlorous acid. Consequently, the Cl0 minus ion acts as a weak base in water, as in this equation 16.37, and with this value of Kb. Now in figure 16.5, we saw that bleach is quite basic. pH values between 12 to 13. Common chlorine bleach typically 5% of NaOCl solution. Now let's look at sample exercise 1616 using pH to determine the concentration of a salt. Solution made by adding solid sodium hypochlorite NaClO to enough water to make 2 liters of solution has a pH of 10.50. Using the information in equation 16.37 on the previous page, calculate the number of moles of NaClO that were added to water. لاحظوا here we are given here the pH of 2 liters of solution NaClO and must calculate the number of moles of needed to raise the pH to this value. Now NaClO is an ionic compound consisting of Na plus and Cl0 minus ions. As we said before, Na plus is a spectator ion, it does not affect the pH. So it is a strong electrolyte that completely dissociates in solution. Now Cl0 minus ion, which is a weak base with Kb equal 3.3 times 10 to the minus 7. Now from the pH we can determine the equilibrium concentration of OH minus. So pOH equal 14 minus pH and pOH equal 14 minus pH and equal 14 minus 10.5 equal 3.50. The molar concentration of OH minus equal 10 to the minus 3.50, so 3.2 times 10 to the minus 4 molar. Now we can calculate the molar concentration of OH minus by using either equation. We will use the later method here. We put the equation and then we construct the table. Now Cl0 minus X molar and this 0, 0. So the change is minus this amount plus this amount plus the same amount. Then equilibrium will be X minus these amounts. Then we plug it into Kb expression, equilibrium expression, and then we can calculate X, and this X will equal 0.31 molar. We may say that the solution is 0.31 molar in NaClO, even though some of the Cl0 minus ionized have reacted with water, because the solution is 0.31 molar in NaClO and the total volume of solution is 2 liters. 0.62 mole of NaClO is the amount of the salt that was added to water. Then you can also solve this practice exercise. Now, relationship between Ka and Kb. Now this table here shows us some conjugate acid-base pairs with the Ka and Kb value. We have seen in a qualitative way that the stronger acids have the weaker conjugate bases. To see if we can find a corresponding quantitative relationship, let's consider the NH4 plus and NH3 plus conjugate acid-base pair. Each species reacts with water. For the acid NH4 plus, the reaction is, and for the base it is. You can see them in the book. Now, and each equilibrium is expressed by dissociation. So at the end, we conclude that Ka and Kb are related in this way. Ka times Kb equal Kw Thus, this product is the ion product constant for water, Kw. We expect this result because adding the two equations give us the autoionization equilibrium for water, for which the equilibrium constant is Kw. So again, this relationship is so important that it should receive special attention. The product of the acid dissociation constant for an acid and the base dissociation constant for its conjugate base equals the ion product constant of water, as you can see here. Therefore, if you know one of them, you can calculate the other. Let's see this sample exercise 16.17, calculating Ka or Kb for a conjugate acid-base pair. Calculate A, the base dissociation constant Kb for the fluoride ion, and B, the acid dissociation constant Ka for the ammonium ion. Now, Ka for the weak acid HF is given in table 16.2 and appendix D as Ka equal this. We can use equation 16.40 to calculate Kb. Kb equal Kw divided by Ka, and this is the value of Kb. Kb for ammonia is listed in the same table, and D also to be this value. And using the same equation, we can calculate Ka to be equal to Kw divided by Kb, and this is the value of Ka. Now, if you look up the values for acid or base dissociation constants in a chemistry handbook, you may find them expressed as pKa or pKb, and also we can take minus log Ka or minus log Kb, and the equation can be written in terms of pKa and pKb by taking the negative log of both sides. So again, pKa plus pKb equal pKw, and this equal 14 at 25 degrees centigrade. Now, acid-base properties of salt solution. An anion's ability to react with water. Now, anions are bases. As such, they can react with water in a hydrolysis reaction to form OH-, and the conjugate acid, thus increasing the pH, it will be basic. Now, a cation's ability to react with water. Polyatomic cations like NH4+ are or when containing one or more protons can be considered the conjugate acids of weak bases. The NH4+ ion, for example, is the conjugate acid of the weak base NH3. Thus, NH4+ is a weak acid and will donate a proton to water, as you can see here, producing hydronium ion and therefore lowering the pH of the solution acidic. Many metal ions react with water to decrease the pH of an aqueous solution. This effect is most pronounced for small highly charged cations like Fe+3 and Al+3, as illustrated by the Ka values for metal cations in table 16.6. Now a comparison of Fe+3 Ka equal this value and Fe+3 Ka this value. The table illustrates how acidity increases as ionic charge increases from +2 to +3, because the higher the Ka value, the stronger is the acid. Combined effect of cation and anion solution. Now, to determine whether a salt forms an acidic or a basic or a neutral solution when dissolved in water, we must consider the action of both cation and anion. There are four possible combinations. If the salt contains an anion that does not react with water and a cation that does not react with water, we expect the pH to be neutral. And examples here like NaCl, PaNO3/2, and RbClO4. Now, if the salt contains an anion that reacts with water to produce hydroxide ions and a cation that does not react with water, we expect the pH to be basic, like NaClO, RbF, and BaSO3. Now, if the salt contains a cation that reacts with water to produce hydronium ion and an anion that does not react with water, we expect the pH to be acidic, like NH4NO3, AlCl3, FeNO3/3. Now, if the salt contains an anion and a cation both capable of reacting with water, both hydroxide ions and hydronium ions are produced. Whether the solution is basic, neutral, or acidic depends on the relative abilities of the ions to react with water, such as these examples. NH4ClO, AlCH3COO by 3, and CrF3. Now let's see this sample exercise determining whether salt solutions are acidic, basic, or neutral. Now determine whether aqueous solutions of each of the following salts will be acidic, basic, or neutral. لاحظوا if we take A, BaCH3COO by 2. Now this solution contains barium ions and acetate ion. The cation Ba plus 2 is an ion of one of the heavy alkaline earth metals and will therefore not affect the pH. The anion is the conjugate base of the weak acid and it will hydrolyze to produce OH-, so the solution is basic. Now in the second example, NH4Cl, this solution contains NH4 plus and Cl minus ions. NH4 is the plus is the conjugate acid of a weak base and is therefore acidic. Cl minus is the conjugate base of a strong acid and therefore has no influence on the pH. Because the solution contains the ion that is acidic, NH4 plus, and one that has no influence, the solution will be acidic. In the third example, this solution contains these ion and cation. This is the conjugate acid of a weak base, amine, and is therefore acidic. And again, Br minus is the conjugate base of a strong acid, HBr, and therefore pH neutral. Because the solution contains one ion that is acidic and one that is neutral, the solution will be acidic. Now the last one here, or D here, KNO3, both of them, they come from strong acid and strong bases, so neither of them will react with water and the solution will be neutral. Now in the last one here, the solution contains Al plus 3 and ClO4 minus ions. Cations such as Al plus 3 that are not in groups 1A or 2A are acidic. The ClO minus ion is the conjugate base of a strong acid and therefore does not affect, so the solution will be acidic. Now also you can look at this practice exercise and solve it by yourself. Predicting whether the solution of an amphiprotic anion is acidic or basic. Again, predict whether the salt will form an acidic solution or basic solution on dissolving on water. لاحظوا we analyze. لاحظوا here we need to evaluate each ion, predicting whether each of acidic or basic, because an A plus is a cation, it does not affect pH, and its spectator ion. Thus our analysis, we need to consider the fact that this can act as either acid or base. So this equation acting as proton donor, so here acting as a proton acceptor base. Now the reaction with the larger equilibrium constant will determine whether the solution is acidic or basic. Now the value of Kf for equation, this one as shown from the table, is 4.2 times 10 to the minus 13. We must calculate the value of Kb for equation this from the value of Kf for its complete conjugate acid. And we have this relationship. Okay, so Kb times Ka equal Kw equal this, and because Ka for H2PO4 is 6.2 times 10 to the minus 8, we calculate Kb for this to be 1.6 times 10 to the minus 7. Now this is more than 10 to the 5 times larger than Ka for H2PO4 minus 2. Thus the reaction shown in equation 16.46 predominates over that in equation 16.45, and the solution will be basic. Thank you. End of part 3.